It's the holiday season and I'm in that spirit, so I decided that today should be a bit more special than usual. So I have this double integral, a very fascinating double integral in front of me, and it yields some very brilliant results. Now, we'll get to those results by the end of the video, obviously, but I decided to take a page out of Michael Penn's book for a change. Normally, I don't do this, but he elaborates the tools and concepts, or he at least lists them down before actually getting into the mathematics. So I'm just going to do that for the purpose of this video because there is so much going on here. There is so much going on, as the title of the video suggested. So the tools and the concepts involved are a Weierstrass substitution, fairly simple. This really aggressive substitution that is wonderfully useful at times. I'll get to that in a while. And we're going to show how the results of our integration are connected to the Reimann Zeta function and produce an absolutely gorgeous result that is really hard to believe at first, but it looks absolutely amazing. It's absolutely beautiful. Okay, so now for the exciting stuff. Let's begin our integration. So we have a double integral from -1 to +1 and 0 to 1 of a fascinating looking function. Integration first with respect to x and then with respect to y. So let me carry out the integration with respect to x first, and I'm going to call this I sub x, which is a strange notation, I get that, but let's just go with it. So I sub x is the integral from 0 to 1 of 1 by 1 plus y times x times 1 minus x squared. And the key thing here is that we're integrating with respect to x first, so we have to hold y constant. And y, we see that it belongs to this interval, the interval from negative to +1. So how exactly are we going to go about our business? First up, let me introduce a substitution, a fairly simple one. Let x equal to the sine of t, which implies that dx equals the cosine of t. And how does this actually help? Well, this means that I sub x equals, now how do the limits transform? As x approaches 0, t must approach 0 as well, and as x approaches 1, t should approach pi by 2. And upstairs in the numerator, we have cosine of t times dt divided by 1 plus y times the sine of t multiplied by, now this will become a 1 minus sine squared t, which we know is the cosine squared, the square of the cosine of t, and there's a square root 2 evaluates to the cosine of t, and these terms cancel out quite nicely. So we're left with the integral from 0 to pi by 2 dt by 1 plus y times sine of t. Now, the integral that we have here can be evaluated quite easily using the Weierstrass substitution. So let me first pick a different color, and let's perform that substitution where we let the tangent of t by 2 equal to phi. And we know that this implies a lot of stuff, right? It implies that the sine of t will become 2 times phi divided by 1 plus phi squared. And of course, the differential element dt becomes 2 times d phi by 1 plus phi squared. So this implies that I sub x equals the integral from 0 to 1. Yeah, because as x approaches pi by 2, we have pi by, as t approaches pi by 2, we have tangent pi by 4, so phi will approach 1. So we have 2 times d phi divided by 1 plus phi squared, 1 plus 2 times y times phi divided by 1 plus phi squared in the denominator. And we can multiply upstairs and downstairs by this term 1 plus phi squared anyway, so that simplifies things a lot. We now have the integral from 0 to 1 of d phi divided by 1 plus phi squared plus 2 times phi times y. Okay, so the integral is starting to look better, and it gets even better, to be honest. It gets even better once you perform a completing square process in the denominator. So in case you do that, you do notice that we have 1 plus, we have phi squared plus 2 times phi times y. So all I need now is a plus y squared. But we still have this 1 here. And of course, I'm going to have to subtract the y squared as well. And just for making our life easier, we're going to consider this to be the square root of 1 minus y squared squared. So all of this is now phi plus y squared plus some constant 1 minus the square root of 1 minus y squared squared. Now, before proceeding further, we should note the holiday miracle that I in fact remembered that I forgot this factor of 2 here. So anyway, let's perform another interesting substitution where the structure of the integral is prompting me to say that let phi plus y is just a constant in this case. So let this be equal to u. We have performed lots of substitutions by now, but to be honest, it is kind of fun. It is kind of fun. So under this substitution, we have I sub x equal to twice the integral from y to y plus 1. Okay, cool. Du up here, definitely. And downstairs, we have u squared plus 1 minus y squared, the square root of it, and squared. So this is just a similar structure. This is exactly the same structure as the integral with respect to x of a squared plus x squared, where a is just some real number. So this is obviously the inverse tangent. So we have twice 1 minus, we have to divide by this constant, of course. Okay, see, it did make life much easier. Or even you could have just dealt with this later, but I just liked visualizing it as a separate constant that we don't have to worry about at all. And the inverse tangent of u divided by this constant. And the limits of integration were y and y plus 1. And let me just erase this now. So once you plug in the limits of integration, you have 2 divided by 1 minus y squared, the square root of it. This is a constant term, right? And you're left with the inverse tangent of y plus 1 divided by 1 minus y squared minus the inverse tangent of y divided by 1 minus y squared. And what you have can be evaluated using some basic trigonometry. And we have this relation for inverse tangent of x minus inverse tangent of y. And this equals the inverse tangent of x minus y divided by 1 plus x times y. So I'm not going to go into the algebra of it, and I'm just going to write down the result. And you can try it out for yourselves if you want. And do let me know one thing. I've never used this yellowish color before in doing any mathematics on this thing. So let me know whether the yellow seems okay-ish, or should I drop it completely or just use it occasionally. So what you have now is the inverse tangent of 1 minus y divided by 1 plus y in a square root. And this is, again, not exactly very daunting, to be honest, because all of this, provided that y belongs to this interval, which it does, so check, and then all of this will be equal to the inverse cosine of y. So what you're left with is the inverse cosine of y divided by this term here, 1 minus y squared. And so this is the result of the integration with respect to x. And remembering that our original double integral was this integration result integrated between negative and positive 1 with respect to y. So this is the inverse cosine of y divided by 1 minus y squared. And this is quite elementary. If you just pop in a couple of negative signs, then you have the inverse cosine function as well as its derivative. with the minus sign included, of course. So you can use the power rule. So we have a negative sign outside, inverse cosine of y squared divided by 2, of course, with the limits being negative and positive 1. So plugging in the limits, that will give you, if the inverse cosine equals 1, then that means you have a 0 minus pi squared by 2, correct? So the results of our integration are quite beautiful. It's pi squared by 2, which is quite a nice result. But now for the interesting stuff. Okay, so now for the really cool stuff. And funny thing, I actually paused recording midway to watch the final of the FIFA World Cup, and wow, it was an amazing final to the biggest competition in sporting history. And honestly, this particular final, I mean, Argentina were dominant initially, but later Mbappe really inspired France, and I take nothing away from Mbappe and France. But honestly, this final, this particular matchup, it was almost like a fairy tale. It had a fairy tale ending where everything just fell into place at the perfect time, and I don't think we have the right words to actually describe it, but it was beautiful. It was symbolic of why this is the beautiful game. Lionel Messi, the greatest of all time, wins the FIFA World Cup in his last ever World Cup appearance. And I'm still struggling to believe this. It's like I'm still struggling to believe that this was reality. I mean, everything just fell into place perfectly, just perfectly. And it was brilliant. It was awesome. It was amazing. Anyway, so the really cool part about our integration, to get to that, first up, okay, we see that our integral I is in fact convergent. So if it's convergent, that means I can switch up the order of integration. So I can now integrate first with respect to y, and then later with respect to x. So what exactly is the utility of this switch up? Well, you'll find out about that we'll find out about the utility of the switch up shortly, as it leads to a wonderful result. So yeah, it's worth the wait. It's worth watching till the end of the video. Anyway, so if we switch up the order of integration and I introduce the notation similar to what I had done earlier, I sub y equals the integral from -1 to +1 of 1 by 1 plus y times x times the square root of 1 minus x squared, integration with respect to y. Now here the x terms are all constants, so that makes the integration actually pretty simple. All I have to do is multiply downstairs and upstairs by the constant x. So what I'll have is the natural log of 1 plus y times x divided by this constant x times 1 minus times the square root of 1 minus x squared, and the limits of integration are negative and positive 1. So using these limits, we can write I sub y as the natural log of 1 plus x minus the natural log of 1 minus x. And we can make use of the properties of the natural logarithm to make this result even better. But I'm going to combine these two natural logs with an extra negative sign. So I'll have the natural log of 1 minus x up top and 1 plus x in the denominator. And all of this is divided by x times 1 minus x squared. And now, remembering that we had to integrate this with respect to x, with limits being 0 and 1, so on the left side, all you have is the integral I, our original double integral. And on the right side, you have the negative of the integral from 0 to 1 of the natural log of 1 minus x divided by 1 plus x divided by x times the square root of 1 minus x squared, integration with respect to x, of course. And now this integral may seem daunting, but there's a very overpowered substitution that we can use here, which yields amazing results when applied correctly. And the substitution that I'm talking about is where we let 1 minus x divided by 1 plus x equal t squared. And you must be wondering, like, what the hell? And how exactly is a substitution like this actually going to make our life easier? How is it going to give us an integral that's easier to integrate? Well, first up, let's study the properties of this function phi of x equals 1 minus x divided by 1 plus x. Now, the cool thing about this function is that it is its own inverse. So if you have a function that is self-inverse, that implies that you can switch up the variables without altering the structure of the function. So you have an expression for x as well, which is identical to the expression for t squared. So that takes care of the x term here. And this also helps us evaluate the differential element. So the differential element works out to be negative 4 times t divided by 1 plus t squared squared. And this term here in the square root works out pretty nicely too under the substitution, because 1 minus x squared is nothing but 1 minus t squared by 1 plus t squared squared. And this works out quite nicely to 4t squared divided by 1 plus t squared squared. And this may seem a bit daunting again, but because of the square root, our lives are once again much easier. We have 2 times t divided by 1 plus t squared. So now that we have all our ingredients ready, we may now proceed to actually transform or give the integral its transformed look. So we have the integral from the limits transform from 0 to 1 to 1 to 0, which looks quite weird. And we have another negative sign out here. So if I switch up the order of the limits of integration, I'll add another negative sign which cancels out the first. So okay, that looks much better, much better. The natural log of this term here is just t squared, right? So here we have t squared. Then we have this differential element, which is in fact negative 4 times t divided by 1 plus t squared squared. And all of this is divided by x. Now x is 1 minus t squared by 1 plus t squared. And x is being multiplied by this term here, which is 2 times t divided by 1 plus t squared. And that's a lot of stuff for one integral. But things cancel out so nicely here. I mean, look at this term up here and these terms down here. And if you take this 2 as a coefficient of the logarithm using the properties of the logarithm function, then you have the 2's canceling out as well, and the t's cancel out as well. So you have negative 4 outside times the integral from 0 to 1 of the natural log of t divided by 1 minus t squared. Now the integral you have is actually quite easy to evaluate. So just give me a moment and let me just shrink this a little bit to give myself some more writing space up here. So what I have is the natural log of t divided by 1 minus t squared. And I'm going to take the help of some infinite series expansions here. So the reciprocal of 1 minus z can be expanded using the infinite series, where we sum over the non-negative integers, and we're basically summing z to the n. Okay, but for the purpose of this integral here, which will come in handy later, instead of starting your sum at 0, start it at 1, and to include that 0 exponent, use n minus 1. And we don't have a z here, we have a t squared. So replace the z by t squared. So this term here works out to be the sum over n of t to the 2n minus 2, which implies that your integral I equals -4 times the integral from 0 to 1 of the natural log of t times this infinite sum. Now, this logarithm function here, the log function, is independent of n. So you can just slip it inside the sum. And because we know that our integral is convergent, the integral is convergent, so that means the corresponding sum we get when we switch up the summation and the integration operators. When we perform the switch up, the series, the infinite series we get is convergent too, because the integral is convergent. So yeah, that seems, that is obvious, of course. So we're summing over n integrals from 0 to 1 of the natural log of t times t to the 2n minus 2. Now, this integral here can be evaluated quite easily using integration by parts. So once we perform integration by parts, we'll get 1 by 2n minus 1 squared, and you can verify that. It's quite simple. It's a very easy calculation. So we have reduced our integration problem to an infinite series problem, and we know the value of this integral, so we know where this series converges. It converges to pi squared by 2, which is pretty wild, to be honest. I mean, these are integers, right? These are integers, and we're doubling them, subtracting one from them, squaring, reciprocaling them, and suddenly when you add all of them up, you get something that involves pi, which is quite beautiful. Wild, but quite beautiful. And it gets even better. It gets better once you recall that if you sum the squares of all of the reciprocals of the positive integers, you can write this as the combination of two sums, one for the even integers and one for the odd ones. Now, any even integer can be written as 2 times n. So summing over n, this can be written as 1 by 2n squared. And then you have the odd integers as well. And in this case, the odd integers, normally you would write this as 2n plus 1, but here 2n minus 1. Why the minus 1? Because when you plug in n equals 1, you get 2 times 1 minus 1, which is 1. So that covers the odd integer of 1. If you do a plus 1 here, you'll start with 3, which is not the right way because you're excluding one of those odd integers. So anyway, notice one more thing, that this is 2n squared. So this can be written as 4n squared, and this 4 can be taken out of the sum because it's a constant multiple. And once you shift this term to the left, you get 3/4 of this infinite series. And this equals this infinite series, which we know equals pi squared by 2. So if you multiply both sides by 4 by 3, you get pi squared by 6. And what you have here is the Reimann Zeta function evaluated at 2. So here you have an infinite series of the squares, of the reciprocals of the squares, of the positive integers. And when you add all of these terms up, you get something involving the square of pi, which is quite beautiful and honestly hard to believe. But that's precisely one of the exciting things about mathematics. I mean, beautiful results pop up here and there unexpectedly, and that works with life too. I mean, today we just witnessed Lionel Messi win the FIFA World Cup in his final World Cup appearance in dramatic fashion, in thrilling fashion, as if it was meant to happen, as some sort of fairy tale determined by destiny itself. So yeah, things like these are pretty awesome. They're pretty cool. Anyway, I hope you enjoyed the video. Be sure to like and subscribe. Thank you. See you next time.